Let's today we're going to be doing the bridge design and the diagram showing the details of reinforcement of bridge, the details of interior girder. The American Association of State Highway and Transportation Officials has two truck loading specifications. Number one, the H loading, and number two is the HS loadings. Here are the breakdowns of the loads for each loading. The H20 has 8,000 pounds in the front wheel and 32,000 in the rear wheel. And the H15-44 has 6,000 pounds in the front, 24,000 on the rear wheel. Now the HS20 loadings, that's 44, has 8,000 pounds in the front, 32 in the middle, which is corresponding to the one H20 loading, and there's another wheel in the rear, so 32,000 pounds each. And the HS15-44, this is a smaller load, 6,000 pounds in the front, 24,000 each wheels on the rear. Here's the bridge details of the interior girder. As you can see, these are the stirrups going vertical. It's a vertical reinforcement. It is reinforced against the shear. And the stirrups is grouped in three groups: 1, 2, and 3. It has different distances. Closer to the face of the support, there are 13 stirrups, 9 inches center to center, and the total of that from the face of the support is 9 feet and 9 inches. The second group of stirrups has a larger distance. This is 12 stirrups, and at 15 inches center to center, and the total of that distance is 15 feet. The third group of stirrups is five stirrups at 20 inches center to center of the stirrups, and total distance of that is 4 feet and 4 inches. The total span of the bridge from the center line of the support is 50 feet. Center to center of support is 50 feet. I cut the bridge in half right here at the center line of the span, so I can show the details of reinforcement in this portion, and the other portion, the half portion of the girder, is the same. That's why I cut it there, right there. The bottom bars has 3 layers. 1, 2, 3. And the first layer is going all the way to the diaphragm. This is the diaphragm, 2 of them. Okay, from this mid-span up to the support. The diaphragm is 90 degrees with respect to the girder. It's going like this. Okay, they're forming like a cellular square. Okay, there are 3 reinforcements on the bottom bar, layer and 3. And the first layer on top, there are 3 bars. They're all the bars are all number 11 bars. When you read see a number bar, say number 11, it is divisible by 8. It is 11 over 8. Any number bar you see in the structural details, number bar is divided by 8 to determine the diameter of the bar. So this is 11 divided by 8 is 11/8. Number 11 bar, 3 on the top, and the middle bar, 4 of them, and the bottom bar also has 4 bars. They're all number 11, and the very bottom bar is directly embedded up to the diaphragm of the support, diaphragm of the girder, diaphragm of the bridge. The second bar in the middle here, there's a cut-off point. It's not going through there. It's only up to here at a distance of 2 feet and 2 inches from the left center line of the left support. And the third bar is further cut off. It is cut off here, and the distance of cut off from the center of the support is 8 feet and 8 inches. Okay, that's the cut-off bar that we analyze. The reason for that is is the shear. The most critical shear, the largest shear, if you look at the shear diagram here, the largest shear here at the support. And since it's on top of the support, directly on top of the support, the girder is not going to shear there. The most critical shear when you analyze a beam or a girder is a certain distance of 0.3 from the face of the column. This is the most critical shear. This is a heavy shear loaded here. This part is a close approximate distance from the face of the column or support for the bridge. So that's why the first bar is going all the way to the diaphragm. It's not cut off. And now the second bar is cut right here. 2 feet and 2 inches. Because the shear, as you go down from the maximum shear right here, the support, as you go down to the middle span, the mid span of the girder, at the midpoint of the shear diagram, the shear there is 0, so it's getting less and less shear. As soon as you go along the girder, the shear becomes less, so there's no point of this bar to go through the diaphragm. Only the first layer and the bottom, which is heavily tensioned bar. When the bridge is loaded, the heavy tension is carried by these 4 bars here on the bottom. The second layer of the bar is secondary tension, is carried by that as well. And the third bar has a cutoff point. The cutoff point distance of the bar from the center of the lip support is 8 feet and 8 inches. The total span of the bridge is 50 feet, center to center of the support. Okay, so the third layer of the bar, tension bar, has a cut-off points at a distance of 8 feet and 8 inches right here, because there's less shear right here as you go to the mid-span of the bridge. So there's no point of these 3 bars here. There are 3 of them right here to go through the diaphragm. At this point here, the girder is supported with the bearing. There are 2 spans of the bridge, 2 supports of the bridge. One is supported with the bearing and the other one is fixed. it has to be fixed, because when the bridge is in use, the traffic's going back and forth to prevent from the bridge from falling out from the support. The other end of the bridge is fixed, whereas the other end is supported with the bearing. The bearing there's two types of bearing: fixed bearing and expansion bearing. When the other side is fixed, the other side should be an expansion bearing. The expansion bearing works when the girder is subject to an extreme heat. Subject to thermal expansion, the bridge, girder, and slab expands together because they're the same material. A reinforced concrete girder. When subject to extreme thermal expansion occurs, the bridge will move towards the wall. The bridge will move towards the wall. That's why it is supported with the bearing. The bearing has a sliding plate on top and a roller on the bottom to allow the girder to move during thermal expansion of the bridge, so that the bridge can freely move without stressing the girder, without thermal stresses, to avoid that. And here's the joint between the slab, bridge slab, and the approach slab. The slab, before you get into the girder, the bridge, is called the approach slab. The approach slab and the slab of the bridge is provided by two steel angles. The steel angles in between is filled with a joint filler right here. It's filled with joint filler, and that joint filler is a compressible material. Reason for that is when the bridge expands in this direction through the wall, the box wall of the bridge, that material will be compressed. So it has to be compressible material, not a solid material. A joint filler. This is two steel angles here, and the purpose of the steel angle there is primarily to protect the edges of the approach slab and the slab of the bridge from chipping when the traffic is going back and forth through the bridge. Without the angle there, the concrete edge will be chipped, and that's why we provided that with steel angles with the joint filler, which is a compressible material. The stirrups, the stirrups is shaped in U stirrups. This is the stirrups. When you cut the section XX here, this is your cross section. There are 6 girders in this bridge. 1, 2, 3. This is the mid-span. The mid-span of the bridge, symmetrical about the center line of the bridge. So there are 3 girders of the bridge, and the other half is on the other side. The reinforcement of the slab, of the girder, this is, there are 2, okay, for the girder, there are 2 continuous reinforcement on the top for the stirrups to be attached, for the stirrups to hold onto. These 2 is, there are 2 and number 6 bars, 6/8, so this smaller bar, that's a 3/4 in diameter. That's the, and here the carb has three, number 5 diameter bar, and this is the distance of the bar from the underside of the slab is 1 inch, only 1 inch. The slab is 6.5 thick, and the carb going above the slab is 10 inches, and is reinforced with 3 number 5 reinforcement bars right there, both top and the bottom. And this bar here, these 2 bars, the bottom and the top, is a number 6 bar. At the top and bottom bars of the slab is number 10 bars, number 6 bars at 10 inches all the way, from one end to the other end of the slab. This is a slab, okay, and the distance is 1 inch on the bottom as well as 1 inch on the top. The slab is 6.5 inches, and the total depth of the girder is, including the slab, is 3 feet. It's 36 inches. And you can see here, this is the cross section of the transverse cross section of the bridge. And when you're looking in this side here, there's a diaphragm. This diaphragm here, when you cut it here, you're looking on this diaphragm. That diaphragm has 3 reinforcements. This is a number 3 reinforcement, 3 of them, and a number 6 bars in the diaphragm. The width of the carb is 2 feet 2 inches, and the width of the girders, all of them, is 1 foot and 2 inches. The distance between the clear distance between the girders is 4 feet and 4 inches all the way. There are 6 of them. The top and bottom bars, number 6 bar at 10 inches, and the bar is only covered with 1 inch covering. The thickness of the slab is 6 inches. Alright, this is a cross section. Okay, here the layer bars, the bottom bars of the girder, has distances from the underside of the girder. The first bar is 3 inches and 3 and 1/8 inches right here, and the second bar is 6.5 inches from the face underside of the girder, and the third bar is 10 inches from also the underside of the girder. So this is diaphragm, the midspan, midspan on the support, and the other support has a diaphragm as well in the other half. This is half of the bridge. So you see the tension reinforcement of the girder. There's a cut off there because of the analysis of the shear. Because of the shear analysis, that's why they cut there. And the moving load is used for this bridge is HS20, that has 32,000 pounds, both on the rear ends, rear wheels. The front has 8,000 pounds. It doesn't, when the front wheel is somewhere around here, it doesn't produce a maximum moment. The wheel that produces the maximum moment is the 32,000 pounds, the rear. The distance between the distance between the wheels from the front to the middle wheel is 14 feet, and the distance between wheels in the rear wheels of the truck is variable. It is from 14 to 15 feet, 14 to 30 feet. So automatically this distance here is always 14. So if you place 14 here, the other wheel is still here. The load that produces maximum moment for the moving loads is when the 32,000 load, the rear wheel of the load, right here at the midspan of the bridge. This is the influence diagram created by the last wheels right here. When this is in the middle, the midspan, the other wheel should be here. 30 meter is off the is off the bridge. So this is the only position of the wheels that can produce the maximum moment at the midspan of the bridge. This is the influence diagram analyzed as fixed in one end and a roller support on the end because of the bearing. The bearing has a sliding plate, stainless steel sliding plate on top, and a roller on the bottom to accommodate a thermal expansion of the bridge to move in this direction. The wall is the support also, acting as support and a wall and as a retaining wall for the soil around outside the wall right here. This is soil here, and this is acting as support, retaining wall, and we call it as breast wall. Alright. Okay, I want to point out that this reinforcement is continuous, it's not cut. It's continuous, shaped like this. From here there's a U hook here with the other reinforcement, and then it's continuous all the way to the box wall up to here, down here. And the support has 3 reinforcements arranged together, and also 3 layers of reinforcement for the box wall. This is the girder, this is the bearing. So now you know the bearings. You may know the design of a T girder for the bridge. In the building is a T beam, for the bridge is a T girder. For the bridge is a T girder. When you design a T beam, you have to calculate the effective flange of the beam. For the bridge, you don't need to calculate the effective width of the flange. The flange for the T girder is all effective from mid to mid span there, half and half. It's forming a T. The flanges, both sides here, this flange and this flange here, they are all effective. You don't need to calculate the effective width of the flange for the bridge girder. You can design this all the way without calculating the effectiveness of the flange for T girder. Okay, here's a load applied to this bridge. This size of bridge is capable of carrying its 20-44 load right here. This bridge is designed for this H20, H44, and maximum moment occur at the midspan in the bridge. And here are the details. You may know the dimension of your T girder for the bridge, but you may not know how to actually put it into construction. This is the construction details of the bridge. Okay, distance is there, This is according to the code. The American Association of State Highway and Transportation Officials. Okay, this looks support. Yes, it said, yeah, nice to design, you know, dimension, the height, the width, everything, but how you place it in real construction. This is how the construction is going to be for this bridge. The placement of reinforcement, the distances of the stirrups, right there, the transverse reinforcement, they call it, is done using civil engineering theory. I did that so that you will find out the cutoff. There's calculation for that. Okay, civil structural engineering theory calculates that, how far is that to cut this reinforcement, and the third reinforcement as well. It's pretty easy. It's about shear, right? So I think that's the end of the video, and your subscription actually it makes a lot of difference, so don't forget to subscribe. And another thing here, okay, this is the wheels. The wheels has the center line of the wheels to the other wheel is 6 feet. Okay, 6 feet apart. When you design a bridge, the wheel is analyzed as 2 feet from the curb to the center of the wheel. That's the distance. The wheel, that's the position of the wheel of the truck when you analyze and design the T-girder. And see, that is symmetrical load right there. The bridge, the wheel is not directly on top of the girder. The wheel is analyzed to be on top of the girder so that you get the concentrated load right here and design your T-girder. Even it is distant away from the girder, it is analyzed to be on top of the girder. And the reason for that is the slab for the bridge is thick enough and strong enough to transfer this concentrated load due to the wheel, transfer it to the girder. That's how you analyze this. You may be wondering, the actual location of the wheel is not exactly on top of the girder, but it is analyzed to be right here because the slab is thick enough and strong enough to carry the load, transfer it to the bridge. See the flans? It's a very small distance. The distance between girders is only 4 feet and 4 inches, whereas for the beam it can have 5 meter, 6 meter. That is a very it's a very long span compared to the bridge. So that's why no matter where the wheels are, it is analyzed to be on top of the bridge, the T-girder of the bridge. And there you can design and place the load, the moving load going through the bridge right here. And now you have the maximum moment occurring at the mid-span of the bridge. I think that's the end of the video, and don't forget to subscribe. Thank you for watching. Bye.